I'll be honest, I'm ready for summer too. So. I had I'll have to tell you my little adventure. I had a very interesting couple of days. So we didn't have class on Wednesday because I was supposed to be at a conference. I did not go to that conference. What happened was, so when the conference was in California, and when I was buying plane tickets out of here, like Huntington or Charleston, were going to be like $800-900. But for some reason, out of Cincinnati, they were like $350. So I'm like, that's an easy decision. I'll go to Cincinnati. So Tuesday morning, I'm driving to Cincinnati, and I'm on the AA in Kentucky. Between, like, I'm like 25 miles from Grayson, right? So middle of nowhere.
You're probably in Lewis County.
What's that?
Lewis County, where I'm from.
So I hear a clicking.
You didn't hear banjos, did you?
No, although I probably should have. No. I hear clicking, then I hear a rattling, then my car starts shaking, then my car dies. All that happened within like half a mile or a mile. So I was stuck in the middle of nowhere. So I didn't make my conference. So I had to get my car towed back, and I actually just been working at home these past 2 days. So it's been a very adventurous couple days. So I missed my conference. So alas, everybody's like, "Oh, you get to go to California?" No, I didn't get to go to California. So okay, let's get back to CE 414 for our last time together. Can you believe it? First off, if you have not yet done so, scan the code. Everything's up to date. The only homework left that's up to date or that has been graded is 6.8. Homework 7 was due today. No late submissions because the solution should be live today. And did everybody get the at-home game? Everybody get the at-home game? All right. Excuse me. For the course eval, there are 24 students in the class. 17 of you have uploaded proof that you did it. 19 of you have done it, okay? I've assigned bonus points to everybody who's uploaded, but there's 2 of you that haven't uploaded proof. But what I'll say is if I get everybody to actually just do it, I'll just give everybody a bonus point. So if you haven't done the course eval, please do so. Again, you can say I'm the worst professor ever, just please do it. I do take the feedback very seriously. One thing I was talking about right before class is we have 14 weeks of instruction and then finals week. Next year we have 15 weeks of instruction. So I have an additional week. And I'd be interested, for those of you that have not yet done the course eval, I'd be interested to hear what you think I should do with that week. I've debated on a couple ideas. One of them is a project. We never did a project in this class, and part of me thinks, maybe it's time to do one. Although there is a chance I don't teach this course next year. I haven't made up my mind yet. What? What? It's not going to affect any of you all.
Quitter.
I won't allow. I have debated offering a course in design of wood structures and timber design next year. I haven't made up my mind if I want to do that. So I don't know. I haven't made up my mind yet. So timber design is well, let's just say it like this. You better get used to tables, because there's a lot of tables in timber design. A lot of tables and a lot of adjustment factors. So you basically take your reference values for timber and then you modify them by like 8 or 9 different factors for temperature and wet surface and incising and flat use and stability and format conversion and all sorts of load duration and all this stuff. So it's just a lot of factors and a lot of tables. So, but I have been thinking pretty strongly about teaching it next year. So, okay. Exam 3, logistics. So what I want to do is go through the logistics for the exam and then the content, and then open it up for you all for questions. What I'll say is this is no different than any of the other exams I've done. So just because we have 2 hours does not mean I've designed this to be a 2-hour exam. It's pretty much just a regular exam in here. You've just been given 2 hours to take it. Now, column and beam problems do tend to be a little bit longer than their tension member counterparts or what have you, so it's possible that it might take you a little bit longer than an hour, but I have not designed the exam that way. I use my same little rule of three that I've, excuse me, that I've always used. Okay. And for format, one other thing, yeah, so it's going to be, a series of conceptual questions, and then I'll go ahead and tell you it's three problems, three computational problems. So pretty much the same as it always has been. Open book, closed notes, like as in last exam. So I mean, you can use the manual. You do need the manual. You can do a formula sheet, put whatever you want on it. Calculator. I don't care what calculator it is, as long as it doesn't have a Wi-Fi connection. You all know the drill. No different than previous exams. Let's talk about the content. Okay, this is what's on the exam. Okay, so first off, columns. Okay, so for columns, I want you to understand basic buckling theory, and what I mean by that is things like, what is an effective length factor? Like, what do the K values do? Well, what they do is they compare the column against its pin counterpart. So if you have a K value of 2, that means its effective buckled length is twice that of a pin counterpart. What are the two reasons that real column behavior deviates from what we idealize in our theory? And those are geometric imperfections and residual stresses. Remember the idea that members are not perfectly straight or perfectly plumb, and so those imperfections will affect its buckling behavior. And then also from the rolling process, from the manufacturing process of rolled shapes, we have locked in residual stresses from that differential cooling process, and those locked in stresses affect its behavior and stability. Regarding analyzing columns, there are two ways to analyze the columns that I've showed you, method 1 and method 2 that I'm calling. Method 1 is to just use the equations, the AISC column curves, and method 2 is to use table 4.1. And then you need to be able to design using table 4.1 as well. And I guess I should say table 4.1a, because table 4.1a is the 50 KSI table. There are additional tables for different yield stresses. Okay, for beams, okay, I want you to understand the basics of all the theory. So what I mean by that is, so first off, I want you to understand what the difference between the elastic neutral axis and the plastic neutral axis of a beam is. How do you compute ZX? How do you compute MP? Remember, MP is just FYZX. Lateral torsional buckling. And so what I mean by lateral torsional buckling is, I want you to understand that, lateral torsional buckling is the phenomenon of kicking out and twisting. That's the phenomenon that beams experience when they lose stability. So whenever we derived our expression, we needed to consider both the beam deflection and the torsion. Remember, I-beams experience both pure torsion and warping torsion, right? Remember, circular cross-sections do not warp, right? So we have to consider warping when we look at I-beams. Moment gradient. So remember, when we derive our differential equation for lateral torsional buckling, we assume everything is a constant term. And so that makes the math a lot easier when we're deriving that solution. And that's fine for section properties like a moment of inertia or J. It's fine for material properties and what have you. But the one term that we treat as a constant, which we really shouldn't, is moment. Moment diagrams go up and down. And so we introduce this term CB to correct our solution to account for the fact that moment changes, that it's usually not constant. We want to be able to analyze and design beams, and so we handle that either with discretely braced or continuously braced beams. If you can handle a discretely braced beam from analysis, you can handle a continuously braced beam, because a continuously braced beam is just a discretely braced beam with LB is 0. So remember, for continuously braced beams, we're just designing or analyzing using ZX, and for discretely braced, we're using the beam charts. And also, don't forget deflection limits, okay? Those are going to rear their ugly head as well. And that's the exam. The rest of this is just content from the slides that I thought were the greatest hits. So I've got the K values for columns. Remember, we're using the theoretical values, not we're not using the theoretical values, we're using the recommended ones. The theoretical values are just that, theoretical. Okay? Column analysis using method 2. So method 2 is, what we're doing is we're going into table 4.1a and we're saying, okay, If KLX is less than KLY, just look up the capacity. But if KLX is bigger, we look up the capacity based on either KLY or KL effective, and KL effective is just KLX divided by that ratio. That's to ensure those KLs are apples to apples. And there's a good chance in this table you're going to have to linearly interpolate. So I throw in the linear interpolation equation here. For designing columns, we just 1.2 dead plus 1.6 live. We determine the largest KLX and KLY for that column. Once we're in design mode, what we do is we design or select a group of sections based on KLY. So a group of sections is usually 1W14, 1W12, 1W10, and 1W8. Some of those may not be available. Like if you have a really, really heavy load, you may not have a W8. But we at least try and select one of each. And then for each of those, if KLX is, or if KLY is bigger, just pick the lightest one. But if KLX is bigger, calculate the KL effective, verify capacity on each one, whichever one is most efficient, select the lightest one. And then whichever one you pick, make sure you analyze it using the equations. Okay, MP. MP is calculated by taking Fy times Zx. And remember, the way that you calculate Zx is you find the place on the cross section where the area above that line equals the area below that line. Then it's just a series of moments. Area times distance, area times distance, area times distance. So if you have an I shape, it might be 4 moments, right? The top flange, the web above the line, the bottom flange, the web below the line. And for each of those shapes, you have an area and you have a distance from the line to the center of the shape, from the line to the center of the shape. And then just the sum of A times Y will give you your plastic section modulus. And then that times Fy will give you MP. When we're, for the aids that we use, so first off we have table 3.2. Table 3.2 is built off of an Fy of 50 KSI. And what I can tell you is that pretty much for the entirety of the exam, unless it's explicitly stated otherwise, Fy is 50. You may have a problem where it's not, but if it's not, you'll be told that Fy isn't 50. Table 3.2 is probably one of our most ubiquitous design aids for beams. It's the one we use the most, even for discretely braced beams, because it contains our VBFs and LPs and LRs and all that. The sections are arranged in groups, and within a given group, the top row is bolded because that's the lightest section within that group, and so we sometimes call those the economy sections or the economy shapes. And we can also use this table for design. Table 3.3 is the moment of inertia table. So what we do is, this is the table that we use whenever we've gone through and picked a section for moment capacity, and we find that moment capacity is not governing, that deflection is governing. So we just abandon all the beam charts, abandon all the design aids, and just select based on a moment of inertia. Again, I know this table looks like a hot mess, but remember this is just the unbraced or the beam chart. So we just go in on the x-axis with our unbraced length, and on the y-axis we go in with mu over CB. We divide out the effects of CB because this table is configured based on a CB value of 1. For continuously braced beam design and discretely braced beam design, the processes are very similar. It's just you're using different design aids. For continuously braced beam design, you do your structural analysis first, get your MU and your VU. For step 2, you compute your required moment of inertia. One thing I'll tell you is that I will probably, in the land of design, give you the self-weight. I'm not going to make you just randomly guess one. Like, you'll be told, assume the beam weighs 50 pounds per foot, or assume the beam weighs 100 pounds per foot. I'm not going to tell you just make something up, because I want everybody to sort of arrive at the same answer. When you're doing continuously braced beam design, what you do is you take that moment and you just go to table 3.2 and find the section or the lightest section with a PMP higher than that. So you go to you take your MU, go to the PMP column, find that value, go to the next highest bold row, and that's what you pick. That's what you use for continuously braced beam design. For discretely braced beam design, you just go into the beam charts. Now, if you pick a section and you find the moment of inertia is too low, abandon table 3.2 and just go to table 3.3. And then when it's all said and done, analyze moment, shear, deflection. Now for discretely braced beams, we have our moment gradient modifier. This one, so we have this expression for computing the moment gradient modifier. What I'll tell you is that when possible, we would like to look it up in table 3.1. So if you need to compute it, this is how you do it. But if you can use table 3.1, go ahead and use table 3.1. Whenever you have a beam that has multiple unbraced lengths and multiple CB values, choose the segment that has the largest LB or the lowest CB. And usually those are those might be the same segment, or should be pretty easy to determine that. So if you have a beam that has, I don't know, 2 unbraced lengths and they're both equal, just choose the one that has the lower CB. Pretty straightforward. Here's our equations for capacity. Again, I think these are pretty fresh in our head. For design, again, the process is very similar. The only thing is, in step 1, if you're doing discretely braced beam design, you'll have a CB value that you need to get, because when you go into table 310, you're going into table 310 with your LB and your MU over CB. Find your section. If that section doesn't meet deflection limits, then abandon all this and go to table 3.3. Analyze moment shear and deflection. And don't forget the possibility of revisions because of those false positives. That's it. That's pretty much the exam. I'm not going to make you do any shear capacity stuff on the exam, and you shouldn't have any sections that you design where local buckling is an issue as well. So I think we've avoided that in the problems that I've formulated for the exam. So that, ladies and gentlemen, is what's going to be on the exam. The floor is yours for any questions. Yes?
Are you going to give us a problem like 2 times ago, where it's something we didn't really go over and we have to redo the specs to find it?
No. You're talking about the shear homework? Yeah, no. I'm not. That adds time, and I wanted you to have the experience to do that, but not on a test. That's my only question.
You answered mine already. Is it going to be the same length as the old 2 exams, or you know,
It's not going to be longer. I mean, like what I can't do is control if you all just want to take the whole time. What I can tell you is I've given this similar exam to this in the past, and within an hour and a half, most people are gone. The ones that are there, like, choose to be there. Like, I have students who say, I have 2 hours, I'm going to use the whole 2 hours. That's totally fine, It's your time, so use it, I'm going to be here for the whole 2 hours unless I literally have everybody's exam early. Then I'll leave. So. I see. Come on, y'all are letting me off early, easy. There's got to be more questions than that. Or is it really just, I'm just done? Just done with this semester.
That's it, buddy.
And it doesn't help that my exam's on Friday, right?
It's not my last exam, if it makes you feel better.
But how many of you is it the last exam? How many of you is it the last exam you'll ever take? I'm sorry it's so late. I'm sorry it's so late. I got to rush to grade them, so like
I was gonna say, when do you guys have to?
Monday by noon.
Okay.
So, and usually like, so in my role as AD, sometimes I'm having to chase people down, get their grades in. So, but so I actually set up. So I've got all my grading spreadsheets set up already. So I told y'all what I do for grading is, so I have the solution to a problem, and then I have a column for literally every student. And so if it's problem 3 and you make a mistake on step 2, I change the value in step 2 and I should be able to get to the same thing you get. So that way I'm only deducting for that one mistake, right? I've set that up already. I've got my grading report set up. I've got it set up to where I can upload the grades to the Blackboard immediately. So I'm sort of like prepared so that come 10 o'clock on Friday morning, I can just start grading. Because I got to get them done quick. So I also have about 100 CAT CAD assignments to grade that week too. Their final CAD assembly, so that'll be harder to grade than this. So.
If only there were two guys that you could pay to do that.
I know. But for them, I know that they're done this with, like, after this, they're done too, so.
They've clocked out already. As have the rest of us.
I know. But you got an exam coming up, and I can't.
I'll try, I'm gonna try my best.
How many of you have played the at-home game and realized, like, you can dial it in and still pass, and like, oh man, I'll just, yeah.
That's what I was contemplating, actually, if I should do it.
What?
Like, do the at-home game.
Oh, like whether you should, because you're afraid that if you do play the at-home game, that you'll be like, oh, I don't.
I'll play the at-home game, I'm gonna walk in. I'm gonna walk into a vendor.
Any questions at all? I mean, y'all are letting me off easy. Has it been an enjoyable class?
Yeah.
Okay. Any suggestions for next year, or if I teach this class next year? All right. Going once. Going twice. I'll see you next Friday, everybody. I'm going to pull up the code one more time, and that's all I got, everybody. It's been a blast having everybody in Steel tonight. I love teaching this class. I mean, it's my baby, so it's been a blast. So, see ya.